I will now present the work entitled Biaxial Testing of EPDM Rubbers for Use in the Automotive Field, Development of a Fixture for Uniaxial Testing Machines. The co-authors are Matteo Migliorato and Giovanni Meneghetti from University of Padua, and Emanuele, Ghirelli, Claudiu and Matteo Bergonzoni from Fornitec. This work has been performed in collaboration with Fornitec, which is a leading company in the sector of gaskets for sports and super sports cars. In particular, Fornitec designs and manufactures the entire car set of seals, such as seals for doors, windows, glass scraper, trunk, and so on. Fornitec, during the design of such components, observed a lack of correlation between the available results from experimental tests and numerical simulation due to an insufficiently precise characterization of the materials. In fact, Fornitec has generated the experimental results by testing samples only under uniaxial loading. However, such a test is not sufficient to characterize properly the material under a generic stress state. Elastomers are characterized by large deformation under the action of relatively small stresses and shows non-linear stress-strain relationship. They are classified typically as hyperelastic materials, and their behavior is defined on the basis of a strain energy density function, which, when derived with respect to a strain component, provides the relevant stress component. In the literature, several theoretical models are available to approximately express the strain energy density function for elastomeric materials. The calibration of such model must be performed on the basis of experimental results. However, to properly characterize the behavior of elastomers under a generic stress state, uniaxial tensile test is not sufficient, while experimental tests under different and complex loading conditions must be performed, typically combining a uniaxial tensile test with an equibiaxial tensile test. So the aims of this work are to perform a uniaxial tensile test on materials adopted by Fornitec to manufacture seals, to design and manufacture a fixture, to perform equibiaxial tensile test, to derive engineering stress-strain curves of the materials under both stress conditions, and to characterize the materials in terms of strain energy density function, and to compare the results between finite simulation and experimental results. The materials adopted by Fornitec to manufacture seals are EPDM rubbers, which are tear polymers obtained by the copolymerization of ethylene, propylene, and diene. Several EPDM rubbers have been tested in this work, namely dense EPDM, which are classified according to their short hardness, and also sponge rubber. Fornitec adopted different elements to manufacture seals, namely junctions and also drawn products. Junctions allow to connect, to link together different drawn products, and are made only by dense EPDM, therefore EPDM 50 short and 80 short. While drawn products are made both by dense EPDM and also sponge rubber. First of all, uniaxial tensile tests have been performed. However, given the impossibility to adopt specimen geometry according to international standards due to the reduced stroke of our testing machines, several specimen geometry have been investigated. Preliminary tests performed on dog bone specimen and also rectangular ones showed a large slippage of a specimen from the gripped area, and moreover, even when the specimen failed, the failure occurred always at the gripped area or at the fillet radius. Therefore, the dog bone specimen geometry has been improved by increasing the gripped area and also the fillet radius. And in this way, all the failures occurred at the gauge section. Therefore, using such a specimen geometry, we have obtained the engineering stress-strain curves for all the tested materials, and they have been reported in this graph. A dedicated fixture to perform equibiaxial tensile tests being not available in our laboratory, the main aim of this work is to design and manufacture a fixture to be housed in a common uniaxial testing machine. The main requirements of this fixture are to interface, to have a reduced size to interface with an MTS mini bionics axial testing machine, to have a reduced number of components, to ensure orthogonal and equal displacements along two directions in a cruciform specimen, to allow testing cruciform specimen up to failure, and to allow also camera housing for measuring local deformations, and also to have reduced cost. Accordingly, we have developed a system which translates the vertical uniaxial displacement of a testing machine into two orthogonal horizontal displacement applied to a cruciform specimen using cables and pulleys. To measure strains in the central area of the specimen subjected to an equibiaxial tensile loading, a vision system has been developed. First of all, a white indelible marker has been adopted to trace lines and defining a reference square on the surface of the sample. After that, the procedure to measure strains and to link them to relevant stress levels has been performed according to three different steps. The first step is the image acquisition, which has been performed by using a digital microscope placed above the sample to measure the central area of the specimen during the full test. The second step consists in processing the capture frames by using a commercial software provided by National Instrument Vision Assistant, and accordingly we have started from the original image, and we have optimized it by changing the brightness and the contrast to make the markers stand out. After that, the image has been made monochrome by extracting an RGB plane for subsequent processing, and again, then we have applied a filter to highlight the details of the image and also to enhance the H pixels of the markers in terms of brightness as compared to the background. However, such a filter increases also the noise of the image, therefore a smoothing medium filter has been applied later. Then the H pixels of the markers have been detected along the two orthogonal loading direction on the basis of the difference of brightness of the markers as compared to the background. Then, given the coordinates of the markers followed throughout the test, the National Instrument Vision Assistant provides also the displacement of the markers with respect to the reference condition. However, the testing machine and the vision system were not synchronized. Therefore, a synchronization has been performed on the basis of the failure phenomenon, which has been defined with reference to the video system as the frame where the incipient failure was observed, while dealing with the testing machine, the failure phenomenon has been defined on the basis of a recorded load drop. Therefore, synchronization has been performed on this failure phenomenon, and at this point, for each frame, we know the displacement of the markers and also the strains, and importantly, we know also the relevant applied load. So, under this condition, we have performed equibiaxial tensile test on different cruciform specimens made of EPDM rubbers. The stresses acting on the sample has been calculated starting from the load acting on each specimen R, which was equal to a quarter of the total recorded load. While dealing with the strain value, having the displacements of the reference markers over time, we have calculated the strain in the center of the specimen as the average between the strains acting along the x and y direction, assuming a uniform strain field within the reference square. In this way, we have obtained engineering stress strain curves of all tested EPDM materials, and it is worth noting that the strains measured by the DG system along the y and x direction were equibiaxial. However, all specimens failed on one of the arm and not in the center of a specimen where an equibiaxial stress state exists. Therefore, the failure stress and strain cannot be considered as characteristics of a material under equibiaxial loading. Even the use of aluminum plates glued to the gripped area in order to reduce the stress state in that region do not allow to induce failure in the center of a specimen. Conversely, they generate a premature failure. So an optimized specimen geometry should be developed to induce failure in the center of a specimen to get failure data under equibiaxial loading. Having the stress strain curves under both uniaxial and equibiaxial loading, a theoretical model should be selected and fitted on the experimental results to be later adopted on finite element simulation. In this case, the models which better fitted on the experimental results are those provided by Munir-Eglin with 2 or 3 parameters. And it should be noted that, in principle, if the fitting between the model and the experimental results is performed only on a single curve, either uniaxial or equibiaxial curves, the model allows to predict very well the stress state on which it is calibrated, while it can significantly deviate for stress states different from the calibrated ones. So, by taking advantage of a combined fitting available in ANSYS Workbench, we have fitted both models on both experimental results obtained under uniaxial and equibiaxial loading, obtaining a good agreement. And it can be observed that the best model which better fit the experimental results is that provided by Munir-Eglin with 3 parameters. So using this model, we have performed a finite element simulation of the uniaxial and equibiaxial tensile test. I'm close to finish. We have performed a finite element simulation of the uniaxial test and also the equibiaxial one by applying the experimental displacement at failure at one end of a specimen and by calculating the constraint reaction to the opposite end of the specimen. So we have in hand the displacement at failure and also the load applied to the specimen. Therefore, we have derived the simulated load displacement curves for both uniaxial and equibiaxial tensile test. We have compared such curves with the experimental ones. It can be observed that dealing with uniaxial tensile test, the agreement between simulated and experimental curves are very well. Agreement is very well. While under equibiaxial loading, the agreement is fairly good in the first region of the curve for a reduced strain value, while a general trend to deviate has been observed for large strain values. So to conclude, uniaxial tensile tests have been performed up to failure of the cruciform specimens. A dedicated fixture has been designed and manufactured to perform equibiaxial tensile test. A vision system has been developed to measure strains in the center of the specimen. Materials have been characterized in terms of strain energy density function, and the curves from finite element simulation have been satisfactorily compared with the experimental ones. With this, I have concluded. Thank you for your attention.
Thank you, Alberto, for your very interesting presentation. Questions, please?
Thank you for your nice presentation. So like you said, like in the biaxial test, the fracture happened close to the waves.
Yeah.
Right. So we did a study on dual phase steel and mild steel, because it was a different material,
Okay.
of course. But then we did optimize in autoform that along the radius that you have, if you make a further cutout, like as you can see.
Cutout?
Yes.
Okay.
So
Okay.
it's I mean, I can share the reference that you can look out. So that reduces the cross-section area in the middle compared to what you have in the grooves area. So that improves. Maybe you will not go all the way up to failure, but that will improve that how much is the maximum strain.
Yeah, thank you. It is a very good idea, and also people who tested rubbers under biaxial tensile loading in the literature, it is a common specimen geometry that you suggested. However, we had some problems with the company to manufacture such a specimen geometry due to the molds that we adopted to manufacture.
So there will be additional mold that could be cut out. But
Yeah.
it's a matter of optimization depending on.
Thank you very much.
Yeah, but just a complimentary question. I feel like you didn't use digital image correlation for any sort of measurement, because these days free kind of softwares are available. You can
Yes.
do that, and could be really beneficial.
You are right. In this case, we would like to develop a very cheap system, since to manufacture such tables in aluminum alloys and also including the digital microscope, the cost of such a fixture is lower than 1,000 euros.
Also, the hardening curve that you eventually calibrated probably would be nice to do an inverse calibration to the simulation. Maybe I can discuss with you later. Did you have a separate hardening curve for instrumentation and biaxial was the same? Maybe you can discuss that.
Thank you very much.
Thank you.
Thank you very much for the presentation. Very interesting work you done. I would like to go to slides 10.
10?
Yes. The simulation you did was elastic simulation or elastoplastic simulation model.
We employed an hyperelastic material model.
Okay.
So the material is elastic
Yes.
and incompressible.
Okay. Okay. The curves down. If you can show that, please.
Yeah, I'm sorry.
Maybe the small difference at the end of these figures compared to the simulations, you can improve the results maybe if you take into account the viscoelasticity of the material. I think is why you have this change in the rates. It can be because I think that it can be because of the viscoelastic behavior of the polymer, because almost the polymers are behave like.
Thank you for the suggestion. I missed also that the material model is isotropic. It is well known in the literature that especially for large strains, rubbers are not isotropic materials. It tends to be anisotropic.
Okay.
It is not included in physical simulation.
It can help to increase the calculation. Thank you very much.
Thank you.
Thank you very much for your talk. I was wondering on the modeling part, which other models you considered for your strain energy function, or how strain energy function, whatever you want to call it?
The models that we have adopted.
Yeah, because the Moody-Rivlin model, it's a phenomenological model. I wonder if you considered microstructurally based models, which account for chain orientations and this sort of things.
We have checked that we use ANSYS Workbench as a finite element software. We have checked the different models available in the material database, but I have not found microstructural based models to define the strain energy density function. We are, for example, Yale model, which is already, again, phenomenological. Ruda Boys is available in ANSYS and some others, but according to my knowledge, no microstructural based models are available in internal software. So we have not tried to adopt also such models.
Thank you.
Thank you very much.